Okay, let's get started. So today we will have a short class. Then after the lecturing part, we will do some in-class exercise. There's a challenge I want you guys to hack. I will work around to help you guys. Okay, so last class we talked about how we can put share code in some other places. So, but basically we're still putting share code onto the stack. It's not necessarily through the buffer overflow directly. We put the share code on the stack. We put share code in environment variables, in command line arguments. I didn't show you how to do that in command line arguments, but you will do that in the homework next week. It's the same idea, right? So I want you to figure it out. So today we're going to look at a little bit more challenging topic. So we will not be able to overwrite directly the return address on the stack in today's challenge. Instead, we can only overwrite the saved EVP or RVP in this case. We're going to use the same share code we used before. So during this class, also in the CTF, you can directly use those share codes. You just copy from the slides, then you can use it. So the attack we are going to look at today, we can call it a frame pointer overriding attack, because the saved EVP is the frame pointer. EVP points to that, we're going to only override that. So 4 bytes higher than that in 32-bit immersion will be the return address. We will not be able to override that. So this is the program we are going to hack today. So this program has a main function which takes 2 command line arguments. If it's not 2, just return. Then it has a val-foo. Val-foo will call memory copy. Okay, so now we have another vulnerable function. Memory copy itself actually has a parameter to indicate how many bytes you want to copy. So this is slightly different from string copy. String uncopy, you can do that, but it doesn't mean if you use a safe version of the function, like memory copy or string uncopy, your code is free of bugs, right? It's still possible that you are copying too many bytes than the buffer. In this case, the buffer we're asking for only 4 bytes, and you can say that we're copying at least 12 bytes, okay? So as long as the compiler is not generating 12 bytes for the buffer, we're overriding something else. So this program, obviously, there is no print flag function in it, which means you need to inject the share code into the address space. In this case, we can put share code onto the stack. So far, the stack is executable. So that's basically the program, very simple. The only difference is the main copy part, memory copy part. We used to use string copy, but that's basically the same thing. The main difference is the buffer size. The buffer here is very small, okay? In the last 2 weeks, the buffer you're looking at is much bigger, 30 bytes, 48 bytes. Here, only 4 bytes. And the memory copy here is not copying as much data as you want. In the previous example, we were using string copy and also gets. So basically, we can copy as many bytes as we want because gets were stopped at a new line, which is 08, 00, something like that. So, but as long as our data doesn't have 08, we'll keep copying. So here, it will only copy 12 bytes, okay, which means we cannot put share code at a higher address than the return address, which is what we did last class. Okay, so let's take a look at the disassembly of this program. we find the memory copy function. The memory copy function has 3 parameters. The destination, which is the buffer we're copying data to, then the source, then the number of bytes we're copying. So the first parameter, if we do a backward search with the first push, here we say it's actually the last push, will be the destination, in this case, EAX. So EAX has an address of, has a value of EBP minus 8. Okay. Which means at the C code level, we ask for 4 bytes of buffer, but the compiler in this case actually give us 8 bytes. The buffer is here. From buffer to save the EBP, we have 8 bytes. Then the second parameter is the source, and the source is EBP plus 8, which will be the, let's say the EBP plus 8 will be the first argument of Overflow, and which is the string you put in the command line. Right? Then the third argument is C, which is 12 bytes. Okay. So there is an overflow. However, you can only overflow the saved EBP, because from here you can only overflow 12 bytes. Right? So then let's say what will happen if we overwrite those 4 bytes, and how we can exploit that. Now we know that we cannot overwrite the return address. That's what we have been doing. Okay. But so first of all, what is the value at this 4 bytes? That's the saved EBP. That's actually the EBP value of the caller function of the current function. The main function calls Overflow. So when main function calls Overflow, the main function's ON EBP value is saved here. And that EBP points to the main function's ON stack frame, which is somewhere up there. Right? So by changing this value, it means when Overflow returns, we are popping this value or something related to this value back to the EBP register. Then actually this value will be popped back to the EBP register, and the main function will use this value of its base address for its stack frame, right? So let's say if we overwrite like this, we just put some garbage there. We put 4 A's there, okay? 4 A's there. Then when the Overflow returns, what will happen? Did we override the return address? We didn't, right? We didn't override the return address, which means when Overflow returns, we will be getting back to the main function successfully. Okay? However, the EBP's value will not be the original EBP's value. Now will be 4 A's. Okay. Then after that, we will go back to the main function. We will go back to the instruction right after the call Overflow instruction. Then let's analyze what happens here. Okay. So when we do this return, previous return, we're not going to get a segmentation fault. No errors yet. Okay. So the next instruction we have in the main function is AND ESP4 instruction. So previously, ESP points to, after return, ESP points to the parameter, okay? Because before that, the return, when we execute the return instruction, ESP points to the return address. After that, ESP increments 4 bytes. So ESP actually points to the first argument here, right? Then we add 4 bytes on ESP. This is actually the main function trying to balance the stack. Before calling Overflow, the main function push that parameter there. So after the call, it's trying to get the space back by adding this. So this add here is the reverse operation of the push here. So after that, ESP will point to this place. So after that, we move 0 to EAX because the main function is going to return, and the return value is 0. That's why we put 0 into EAX. After that, we're going to have the leave instruction, which is equivalent to those two instructions. Move EBP to ESP, pop EBP, right? So we already know that the main function is called by another function, called by the underscore leave say start main function. So that function calls the main function. So eventually the main function will also return to that function and keep executing. And technically after that, the business logic of your program is done. So that library function will just to clean up something like that, right? But here we're going to return to this. The leave is move EBP to ESP. So at this point, our EBP has a weird value. A value we override, remember? Right? So now we move EBP to ESP. So ESP also has that value, 4/8, right? But still, this step, there's no segment 4, right? We are not accessing any illegal or unmapped memory. So there's no segmentation 4. After that, we have a pop EBP. Okay, this is the tricky part. Because EBP still have the value of 4/8. The pop here, yeah, this is the tricky part. Because when we do pop, we're popping from which place? We're popping from where ESP points to, right? And ESP right now points to a random place. And we're putting whatever at that random place to EBP. That's a random place in memory. So that will be a memory access. And we may access a memory address which is not mapped, which may generate the segmentation port. So in this case, if it works, EBP should have the value at that memory location, and the ESP will increase by 4 bytes. So if we have 4 A's, then now it will look like something like AAAE. Okay? So look a little bit weird. When you look at something like where is it from, right? But it's actually from this port. So this part, we just put 4 A's there, we will get the segmentation port. So after that, we are going to return. If it works, if it doesn't generate segmentation port, we keep running, we have a return. Then what will be the return address? The return address will be wherever ESP points to, right? But ESP now points to AAAE. So we're going to dereference the value there. So there's another chance for segmentation port. Okay, so how do we exploit this? Any idea here? How do we exploit this? Our goal is still to get the flag.
Would we be planting another one of those structures of sled leading up to code to open the shell?
Okay.
And try to overwrite the EBP to where we think the sled will be in memory?
Okay.
That's my guess.
It's the right direction.
Okay.
But maybe you're missing one level in the middle.
I'm sure I am.
Yes. So what we have is, let's say, this is a stack. Okay. This is a high address. This is no address. And let's say this part is volatile stack, and the higher address will be the main, right?
Yes.
So the EBP, when volatile executes, the EBP points to save EBP and return address, right? Look like this. And this address actually points to somewhere here, okay?
Yeah.
So the value is the address of this. So this is the main functions stack ring. Here we have also another saved EBP. They have different value, then there will be a return address, right? And this return address points to somewhere in the main code. Right? This return address is the address of somewhere libc. Let me just call it libc main, right? That address. So now we are going to override this. We cannot override this. We cannot override anything above. Right? So this address actually points to a data structure. We can consider this whole thing as a data structure. The data structure has two things. The lower 4 bytes is the saved EBP. The higher 4 bytes is the return. So what we really want to override is the return address. This one.
Yeah.
We will not be able to override this, but we will be able to override the structure of this. So because we can override this, we can, we do not make this pointer points to this structure anymore. Instead, we make it point to another memory location where we can control, right? There are many places we can control. Go ahead. Why don't we override the return address? Because the vulnerability, the bug here, will not allow us to do that. The bug here only allow us to overwrite 12 bytes. Here. Yeah. Yeah. The bug only allow us to write here, not here. Now, we're going to change this to another place. A place we can control. Now, at this place, what do we feel? We can feel what? So this, first of all, what we are pointing to will be a data structure, not directly to the share code, right? Like you said, a pointer to a share code. So it actually points to at least this 8-byte structure. So this will be saved EBP, but the value doesn't really matter, right? Doesn't matter. But this one, we need the address of share code. Make sense? And so this one will point to our actual share code. So for both of this, so this one share code we have like 30 bytes, 40 bytes. So we know where to put this. We put this in environment variable, command line arguments, right? Those two places. Oh, where do we put this one? Here we need technically we only need 4 bytes, right? Those 4 bytes we're not writing. Yeah, go ahead. Yes, exactly. That's one of the places we can do. What else? We can put this 8 bytes in a buffer. Okay. Where else? Yes, exactly. Right. So we can also put this in environment variable. Right. Okay. So let's try the second approach first because it's actually easier. Go ahead. Also the saved EBP, but the value doesn't really matter because this saved EBP, if the main function returns successfully to libc start main, this EBP, saved EBP will be used of the EBP value. Yeah, so when libc start main returns, it will use this one as its frame pointer. We don't need this. We don't need to overwrite it. But that is the structure we're pointing to. Okay. That's something we cannot control.
Right now we are overriding the main. We went from the EBP that the same EBP address.
Yes.
We have that EBP of the main and there we are overriding another EBP, right?
Yes, we're only overriding this part. Yeah.
No, I'm saying that you said from EBP we went to the main EBP and there we are overriding.
No. For overwriting, we're only overwriting this part. So those two parts we just inject into the address space.
I'm not understanding what's the point of the 4 byte EBP.
This 4 bytes?
Yeah.
because that's what the stack frame looks like. It's not something we can control. Yeah. Okay, then what other challenges we have for this? This one, we can put it into environment variable, and we can use that. I have a command for you, the get environment, 32-bit, to get roughly where this is at, right? We can put a huge knob there, then to increase our chance. So then we can have an address where we will be pretty confident what address we can use for this. Then how about this address? We also need this address. We need to put this address in here. And this address should be very precise. This address doesn't have to be precise, right? Because we have a big knob set. So this one looks like it has to be very precise. So how can we, what tricks we can play so we do not have a precise address? Yeah. Okay. Okay, so what you are saying is we have many of those address of share code, right? We have many of those. We have many of those. We can have thousands of bytes. Then we just point to somewhere random. Right? If we put it somewhere random, then wherever we point to, those 4 bytes will be interpreted as the saved EBP. But it doesn't matter. Okay, so that address probably will be address of share code, but it will be interpreted as a saved EBP. Doesn't matter. But the higher 4 bytes will be integrated as an address of share code. Another problem is, so we only need to try basically 3 times. Offset 1, offset 2, offset 4 times. Then we can get an address that works, right? We don't need a very precise address. Does that make sense? Okay. Well, then let's try this approach. So this is what we're going to do. Okay. We're going to create. So this is not a lob sled anymore. Okay. A lob sled is a low op instruction. Okay. So it's a sled because no matter where you hit, you will keep executing, eventually hit your share code. Here, what we're putting here is not code instructions, but an address. But we're putting so many of that address there. So it's actually something like we can call it. There's something called a spray attack. Okay. So this is something called a spray attack. We don't know the exact location, memory location, we want to put those things on. Even if we put there, we don't know its address. So we were just a spray. We put up so many copies of that in the memory to increase our chance to dereference one of those addresses. So let's say, let's just use the without shell share code here. Oh, I have a, what is the export command here? That this one. Okay. One space here. Next slide. Another one here. Okay, that's it. So we go to challenge, overflow 6, 32 bits. So this is not overflow return because we're not directly overflowing the return address. First, we put the share code. We put the share code There are a lot of. Let me see this one. Oh, you looks a little bit. Oh, that's correct. So this is our share code. Let's move. Let's make the lobster even bigger. So now we have the share code. Now we put the share code into the address space, right? Then try to get the address of the share code. Or S code in this case. Now we have the address. Obviously, this address may be the beginning of this whole string. So, but we have a huge lobster. So we just use address. There's a bigger address, which will be, so we have B8, so maybe something like 8, 9, maybe BA11 would be fine, something like that. So this will be our share code address. Okay, it's in the middle of the lobster, hopefully. Then we need to create this structure. And this structure will look like what? Will just look like, will actually look like just this, many copies of this, right? But after that, we may need to verify the address again. So we do another export. In this case, we don't need the share code. We need the address, which is EA, no, 11 EA FF. Then let's make 500 copies of this as well. Okay, so let's get the both of their address again. Oh, so this address change a little bit. That's good. Oh, sorry. So this is S code. This one, let's do path, whatever. Path. So S code address is still there, which is good. That's we want it to be there. Then path address will be CAF0. Okay. So CAF0 is the beginning of that. So something CAF0, then we can do something CB22. Looks safe that way, right? Okay, this one looks okay. This one looks okay. So this one should go to the saved EBP, right?
Okay, you know, so
Why I'm adding that?
why do you increase the number of
First of all,
that group?
so first of all, this get environment, this program is giving you the address of that environment in its own address space. So it could be different from the environment address in another program, slightly different, okay? Because there could be command line argument, whatever. Okay? So the first reason. The second, even if they are the same address, the address you are getting here is the address of the whole string. So this will be the whole string. S code, equal sign, and those ASCII bytes, the whole string. So even you do that, you will get this address, and that is not your share code. That is just some ASCII characters. So if you start from executing here, it will be illegal instructions, whatever. That's why we have a huge knobs there anyway. Yeah.
What is the value that you're hiding? Okay.
I'm trying to add the several hundred bytes here. For example, here when there was 8, right? Oh, this one, I'm not sure if we were adding too much. So 8, 9, 10. Okay, should be okay, right? 8 is 10, so that's like 500 bytes. Because you change one here, it's basically 256 bytes, right? Yeah. So this one, because our pad is smaller, I'm also adding a little bit smaller. Okay, let's try if it works. So our exploit will look like what? Just 8 bytes of garbage at this address. That's it, right? Let's say if it works. This program is taken from command line arguments. We're going to do Python 2. Say, right? So we have 8 bytes of garbage. Then we have that address, which is 22 CB FF. Let's see if it works. Nope, doesn't. So buffer is at C8. Buffer is at this address. Okay. Where did things go wrong? The address we're using is, we have an export here. This one is C8F0. We use CB. So we have 500 of those. Let's check if we really have them. Right? Environment variable. Path, right, it's here. It's very big. If we get everything correct here. Looks like, so this is path, which is correct. FFPA11. Path should have here 11, right? Oh, okay. What did we forget here? What did we forget here? Here. This one points to this. It's possible that there is a 3 bytes, 2 bytes, or 1 byte off, right? So we need to add that. So the address we're adding here, we should try different addresses. So it should be 22. We can also try 1, 2, 3, 2, 0. Oop, 2, 0, no second and fourth. Okay. But we are not getting a flag. The 3, go to 4. Oh, so see, to 4 we are getting a flag, but somehow 2, 0 we're not getting a flag. Why 2, 0 we're not getting a flag? So to 8 we should get a flag as well. Then, right? Because yeah, to 8 to C, right? To C we should get a flag. 2, 0 we're not getting a flag. If we're doing 1 C, if we're doing 1 C, we're also getting a flag. So only we're doing 2, 0, we're not getting a flag. Why that? What's special about 2, 0? Any idea? But now you see the approach, right? It works. I'm a little bit confused. Why 2, 0 we're not getting a flag? But all other values we're getting a flag. If we have a much smaller value, we have 1 C here. So because that address is CA something. So if we do CA, what is the address? Oh, I don't have it here. That address was CAF0. CAF0. So if it's too small, AAF here, so AAFF may work. Yeah, that's a little bit slow because but this one should work. CB1 say CB20 not giving us a flag. CC20 also. Okay. So I think it's somehow related to 20 here. Why is 20 not giving us a flag? Hmm? Yeah, we can do 30. You want to say if because there is a 0 or something? 30 give us a flag. 40. Yeah. 50, all of them give us a flag. Just 20. 20 is not giving us a flag. Let's say this address will have 20. I'm not sure why 20 is not giving us flag. And it's not easy to debug this as well, because when we debug, everything's address will be changed. Yeah. So well, I mean, our goal is to get a flag. So but why this is not giving us a flag? Is there anything special about 20? We're using memory copy, right? We're using memory copy. Memory copy doesn't really care what value is there, even if it's 0 or copy. But in this case, we only copy that, so it's not related. Well, S-trace will not give us this, and S-trace will only give us system calls, and we already know what kind of system calls it is making, so not really helpful here. One other reason. So this one is not giving us segment faults. So our share code doesn't have an exit, do we? Have an exit segment called on. Oh, this one does have one. So is this one? No, we're not copying this one. We copy this one. And this one. One, okay, we copy this one. So this one does give us. Okay, so there is an exit at the end. That's why for them, we do not get a segmentation fault because at the end of the share code, we have an exit. The question is why when I do 20, we're not getting segmentation fault and we're not getting the flag either. Okay. This is something we can even though we can still debug, we can debug to figure out why 20 is so special. But you get the idea, right? That's the first approach. We use this approach, we can put the share code there. Then okay, the second approach, we can put this address in the buffer. We have the ability to write that 8 bytes of buffer, right? Then let's say this EBP will directly point to the beginning of this. Then the first 4 bytes will be garbage, the second 4 bytes will have the return address. And this program actually print out where the buffer is. So it makes things much easier for us. Right, so this approach, this one we can work. Another way, well, the third way is similar to this. Oops. So actually this one should be lower. So the buffer is still here. Then the EBP, we will have the buffer -4. Then this one points to here. And the first 4 bytes will be the saved EBP value doesn't matter. And this 4 bytes will have the address of the shellcode. This 4 bytes doesn't matter, right? So this should work as well. So to do that, let's first unset those environment variables. Should I use unset? I think the command is unset to make sure the environment variable is not here anymore. Get to hat. Okay, we don't have the panic anymore when we unset. Oh, the shellcode we still use. Okay, so we still have the shellcode. So now what we put here will not be 8 bytes of garbage. We put so let's run this. Now we have the buffer's address. Okay. Oh, this one will also change the buffer's address. How many bytes we're overriding? We're still overriding 12 bytes. So we will have 4 bytes of garbage. Then we will have 4 bytes of garbage. Then we will have a sharecode's address. A sharecode's address will be, have it here, EA11. EA FF. Then we will have the buffer's address, right? The saved EBP now will point to the buffer directory, which we have is FFF B044, right? So if we do this, we also get a flag. And everything here obviously has to be very accurate. 1 byte off, we're not going to get it. Okay. Then if we put the sharecode address in the lower 4 bytes, then we will have this sharecode's address. Then we have another 4 bytes of garbage. Then we will have the buffer's address -4. Okay. So without doing that, we're going to use that 4A as the address, so we're not going to get anything. So there's no segment for it. Oh. What? Oh, when did I remove that? Okay. Okay. So, but with -4 of this, we're getting a flag, right? So that's the 3 different approaches. The third one, second one, actually similar approach. Yeah, the first one. So the second approach and third approach, the reason it works is because we know the buffer's address. But without knowing our buffer's address, the first approach will be more general. You know, we don't need to know. We just put we spray the pad and have a huge offset. Yeah.
Are there situations where the second or third approach are preferable to the first approach?
I think in this case, the second and third approach will be a little bit easier because you do not need the middle layer of that pad.
Yeah.
Right? Yeah, but all those challenges in the class were designed intentionally, right? So it's really hard to tell.
Yeah.
In real production systems, what the vulnerability looks
Yeah.
like, right? Depends on that. Yeah. Okay, so that's the first part of the class today. So let's go over this again. the conditions will depend on to pull off the attack. Now we change a little bit, right? The first ability is still we put the share code onto the stack, but not necessarily just through buffer overflow. We can put them in environment variable command line arguments. The stack should be executable, and we should have the ability to overwrite a return address. And before a return instruction, use that address. Okay. In this case, that return address not necessarily is at its original place. So if we can override EBP, we're actually creating another fake stack frame which has a return address which we can override. Yeah.
In this case, the stack doesn't have to be executable, right? Because you can't, the code isn't in the.
The code is in your stack.
Environment variable.
Yes, that's a stack. Yeah. And we need to know the address of the share code. So the key here is you can say the return address is a code pointer, and that is the address of a piece of code. That's why we call it a code pointer. And as long as that code pointer is somehow different, dereferenced, means the address is called, then eventually we can let the CPU to execute some malicious code. And there are so many different code pointers in the address space. Some of them are not just, they are not return addresses, they're just function pointers. If we can override that and make the program to call that function with an overridden function pointer, then we can still push the program to execute our malicious code. Okay, so in the remaining time of this class, we are going to hack something on this website instead of using our platform. I'm not going to give you too much information there. This is not into this week's homework, but it will be next week's homework. But we can try to hack this. Okay, so this is another CTF platform called Over the Wire, and they have all kinds of binary and other challenges, even crypto challenges. They have like maybe 10 or something, and they start with something simple like command line hacks as well. So what you need to do is we're playing a particular game called Behemoths, and we're playing Behemoths 1, level 1. And I already give you the password for Behemoths 1 here. Okay, so you should start if you just play this game by yourself, you will start with Behemoths 0, then get the Behemoths 1 password, then try to get Behemoths 2's password. So the system is designed this way. There's no flag. Okay, you are just getting the next level's user's password, and the passwords are placed in this folder, etc. Behemoths pass and the name of that user. And obviously, all of those programs, all of those files, password files, they have different users. Okay, like the Behemoths 2, this password file, its owner is Behemoths 2. Then the program you are going to hack is Behemoths 1, which is the setUID program, and the owner is Behemoths 2. So it's actually the same design as our system, just our system only has root and CTF. Here, so you're going to hack this program. After you hack this program, you will be able to, you should be able to crack the password of this. So you can use the share code on the slide. You may need to modify the share code. I'm thinking, so because our share code, if you are directly printing the flag, the flag name is hard coded in our share code. That's /flag. Here, the file name is different. So if you want to use that, you need to change that share code. But technically, you should be able to use the first share code, which gave you a shell. Okay? So if you get a shell, then you can just pass this one, right? So you don't need to change the shell. Yeah, you need to SSH into the server. Yeah. The program, the binary is under root behemoths. Let's try this.
That password is up to date.
Yes. I updated yesterday. Not working?
Not working for me, but I suspect that's more just me not being good at.
So anyone here? You're in, right? Okay.
I'm just,
Oh, here, you have multi-time login behemoth, it should be behemoth.
that's what happened as soon as I connected.
Yeah, but because your user is behemoth, the user should be behemoth one. Yes.
Thank you.
So I'm not giving you any information about this program, right? Then what should you do first? Okay, but even before that, maybe just run the program, use S trace, L trace of tools to get a feeling what it is doing. Because if you just assemble that, it will be huge, be overwhelming. Is everyone in? You're in, right? Yes. Okay. Oh, why did you- So this is a new system, as you can see. Roger. So we are hacking e-commerce 1, this program. I can say this is a steady ID program, like all other programs we have on our platform. And owner was e-commerce 2. That's why the owner. Right? And because of that, if we hack this program, we will be able to read this file, e-commerce 2, whose owner is e-commerce 2. And that will have the password. So now we have e-commerce 1. That's why we should be able to read the password of e-commerce 1. Right? The top password. But we should not have the permission to read the e-commerce 2. We don't have the permission to do that. That's why we're hacking that program. What's the sound? Oh, where? What password? That's our features. We get a buffer overflow something here. Ooh, looks like we do get a buffer overflow, right? So the long password there have a segmentation fault. So maybe there's a buffer overflow. Yeah. Not running any active. One to getting notifications. Looks like it's reading more than 1,000 bytes. Our docker will be smaller than that.
That might have been the actual, but,
Really? It's from here.
oh, never mind.
No. Any idea? What's the probability? Yeah, right. We've gets. What's the probability? Where's the buffer? Give you minus 43. So that's where the buffer is. You override that, your share code should work. Yeah. You have Python on server? Oh, we don't have Python here. We only have Python 3. We don't have Python 2. We do have Python 3, right? Yep, we do have Python 3. I, I remember it's harder than that, more than that. It's working for you? Good. Yeah. So,
But it doesn't have it that extent, we don't have the constant mixed value. It can. I remember I made a doctor. I'm like a 5 times.
final share code.
Ready to be along with. No, like you put the B before the first approach and see that like kind of like. But then when you put it in place to be no, it's the point that first part. Right, but you actually build it out. Oh, yeah, so you know it's a wide thing, large thing, brings the weak and the code. Absolutely, it's start area of like somebody doing.
What?
Or not using when you use it. So I'll share it back.
Not necessarily, because I don't know under the hood how it works. Maybe it's a Docker.
Oh. Alright, and it,
Why not paste the deal? Great, man. Still not working? Oh, okay. All right. Great. Okay. Zero, 1, 2, 3, 0. Weird. I think it's not that simple. That's not the share code I gave. I'm bringing out 31, C0, B0, but it's giving me C3, 80, C2, right? Not that simple. Oh, it's not exactly something.
it's just changing, it's like,
Okay.
for it to be applied to prefix the single forces of B. Or to reference the B when you print. So it's
Like this. Still no. Yeah.
just print that, okay, it prints the B.
Think what?
You can see the B. Using the report. No,
Yeah, I put a B here.
no, but, yeah, but. It's not the whole thing.
Oh, print B? There's a function called print B.
No.
Okay. Yeah, I can't do that.
X value connected. But then it will add the B, will be like this,
All right.
this part.
Okay. So,
Why in if it's
bytes perhaps. Then as is slash X or
you don't use that.
I can use slash X. Right, now. Bytes
No, I don't know.
from X. The function.
I don't use the flash X.
Oh, I don't want to delete that again.
Close. I can't put the slash in. Better if you do it.
Have to change everything. to go away and not have to think them. And problem. And nó equal to that. Oh, you want your line. Oh. Yep. You're on. Thanks. Code on screen, but if you decode on that, then it won't be able to convert. You try to decode and use your face. Remove the bat. What? Remove the ending print. Print. Like this?
No, not that. The print
Remove the thread.
end of ending bracket. Second bracket.
But print is,
Closing bracket.
print is a function, right?
Right, but it returns an empty object.
Oh, okay.
So
I
I
should-
call dot.
I'm missing that. Right? Should be like this.
So remove the. So if you call dot decode on the right, this.
Right.
Right, yes,
Like this.
yeah.
Yeah. The whole thing I should. Yeah, no?
Yeah, so you can't decode it because it's not UTF-8 decode.
Then what if I want to decode anything? Why can't? So if I do this, it would give me this weird thing. So we don't have Python 3 programmer here?
So the only way to do it, you have to use this dot std out dot right.
Okay. Oh, yeah, we can use that too. What's that? I remember that. It's right or something?
Import this, and then you have to use this dot std out dot right.
This dot
Std out.
std out. Okay. Dot right. Okay. So that one I can just use okay. Import this. Import this. First off, std out. Not sure if that's correct, but why is say2 there? Why there's a say2? But we're getting there. There's a say2. That's looks like us. Looks like Unicode, maybe. So how do I change this to ASCII? Oh, I can add a B here. Nope, that one.
Video dot buffer dot right, and then the
Buffer, all right. Then we'll B.
Yeah.
Okay. Yeah, works. Okay, so let's use the same. If you use Python 3, you can use this syntax. Can I write this maybe in our Slack channel? I know most people are using Python 3. If you use other, doesn't really matter. top. Okay. This is not working. Weird. Correct. Okay, so this one is correct. It's right. Okay, good deal. There is a share of this. There's that. Did someone put a share code in? Looks like someone put it there, right? One of us, yes.
Maybe.
Then why there is a S code? You know that?
It doesn't matter.
Right.
I just say we
Okay. It looks like everyone can say the same share code. So, okay, so this command should work for exporting. Yeah. So this one, Python 3 says std out buffer, right? This should work. This should give us a. Can you guys see my environment variable there? I create a new one, DMCS. You guys see that? You can see it? No?
No.
You don't see it? Okay. Then why do I see your S code there? Okay, maybe a different thing. Oh, maybe I did it before. Somewhere. Oh, yeah, I did it before. Yeah. Okay. So this command should work. Oh. You know, stand here. So, okay. Okay, works. Sometimes works. Up the lobster. There. So this one We. Find the share code. Works. Okay, I got it. But not sure. Okay, the syntax work, we can do the share code there. Then use the first share code.
Where I got myself into the whole thing of getting stuck in Python and not realizing barely anything else. Working that I just now doubting Python. Working that's
There's a cat. Remember this guy cat. And so another issue is the buffer not enough, big enough to hold it.
Yeah.
Yeah, so I put it in the.
The method used on the that way that they can use variable.
I debug it.
Okay.
And to give you, then I run through the main function, I print out a string from ESP, because the original stack. You can get a rough idea of what it is.
Okay.
So I use the page, yeah, so I use the 35 under class.
Okay.
You guys will see where I am.
Yep.
So you can even do the below one, but it's a different one. In this case, because the in your circuit in the bucket. Yeah. Now, if the right here. All you have is one. You don't, you are already given. If they don't have a pool, like their environment, the program may give you, so that you can just divide, find the address of the campus. Or you can write your own program. The studio is getting on the way. They can, still be able to write a program and compare in the system. They can get a feel like that. If divide is maybe easier. I must. The new one is from. You disassemble the program, you disassemble. You find there is a 43, remember? What is 43? 43 in hex. So here, well, for 43, which is 67 in decimal, right? So when we have stable EDP, so that's why we get 71 bytes. This is stable EDP. This is a buffer. That's why we need 71 bytes to anywhere before our return address.
In BDD, what are you using to plug in see the full stack?
In GDB, so what I was using is I set a breakpoint as the main function, right? Then I run, so I get there. So where is the stack? The stack is always in ESP, right? So I just exam at 500 strings as the address ESP points to, right? Going, down here, I save the environment variables. Okay. Yeah. Then nice. So it's somewhere here. Somewhere here. Yeah. But this is a very low address. I know when I run a program, the address will be higher than this. So I'm just trying from there, but I make my offset big. So it means much.
Yeah, to be again,
To what?
like how to figure out how to find the environment.
X means exam.
Exam.
500 means I want to find the 500 items. And the S is the type of the item. In this case, is a string. At which address? ESP. Yeah.
Thank you.
Yep.